Every spacecraft humanity has ever built is currently on death row. We just haven't realized it because, in the cosmic sense, we are still holding their hands. We talk about the International Space Station as a triumph of our species, a $150 billion masterpiece orbiting in the absolute silence of the void. But there is a humbling reality we rarely discuss. If you took that station, the most expensive and complex machine ever assembled, and pushed it just a few light years away from the warmth of Earth, it wouldn't just stop working. It would become a tomb within months. Not because of a spectacular alien attack or a cinematic solar flare, but because of a failed $10 pump. It would die because of a microscopic crack in a rubber seal that costs less than a cup of coffee. It would die because in the deep dark between stars, there is no one coming to fix it. We like to think of ourselves as a spacefaring species, but the truth is far more humbling. We are still infants playing in the backyard, never wandering further than the reach of our mother's voice. The International Space Station floats just 400 kilometers above us. To you, that seems like the final frontier. To the universe, that is still breathing Earth's invisible support every single second. Every few months, a resupply rocket arrives like an umbilical cord, bringing fresh food, new filters, software patches, and replacement parts. Behind the crew stands a literal army of thousands of engineers on the ground, monitoring every single breath, every watt of power, and every drop of recycled water in real time. They see the glitches before the astronauts do. They are the ghost crew that keeps the station alive, but a real Starship, a machine built to cross the light years to another sun. It has no mother, it has no backup. It is a sealed, lonely world where every second is a silent, brutal battle against a universe that is trying to turn it back into raw atoms. Move that station past Mars, past the edge of our sun's protective bubble, and every one of those lifelines snaps forever. The silence that follows is not just the absence of sound, it is the absence of a future. Think about the longest any human-made machine has ever operated without a single repair. I'm not talking about a stone monument standing in a field for centuries. That is just a rock. I'm not talking about a satellite coasting in a stable orbit with no moving parts. I'm talking about a real machine. A machine with fluids flowing through high-pressure pipes, actuators firing on a relentless schedule, electronics processing millions of commands, and mechanical gears grinding against each other every minute of every day. The honest answer is measured in decades at best. We simply do not know how to build a complex, active machine that can outlast a human lifetime without someone there to provide a constant supply of spare parts and specialized knowledge. Our entire civilization is built on the concept of maintenance. We fix, we swap, we replace. But in the interstellar void, the word replacement doesn't exist. You have what you brought and nothing else. To understand the scale of this nightmare, we have to look at Voyager 1. Launched in 1977, it is now the most distant human-made object in existence, more than 22 light hours away from its home. It is a triumph of persistence, a tiny, fading whisper in the interstellar dark. But Voyager 1 is a machine the size of a small car. It carries no crew, no atmosphere, and no life support systems. It produces barely enough electricity to power a couple of household light bulbs, and even that power is dying as its plutonium heart decays. Every year, engineers at NASA's Jet Propulsion Laboratory are forced to turn off another scientific instrument, one by one, like putting a patient into a medically induced coma just to keep the brain alive. If we have to fight this hard just to keep a simple radio transmitter alive for 50 years, imagine the complexity of a vessel that has to grow its own food, recycle its own water, and shield a living crew from the relentless bombardment of deep space for a century or more. In the vacuum of space, momentum is free. Once you start moving, you coast forever. But here is the terrifying realization that most science fiction ignores. A dead ship travels at exactly the same speed as a living one. The difference between a starship and a steel coffin is not velocity, it is capability. Can the ship still generate power? Can it still scrub the carbon dioxide from the air before it poisons the crew? Can it still navigate without a ground crew in Houston? Can it still repair the machinery that keeps all of those other systems alive? If the answer to any of those questions is no, then you don't have a starship anymore. You have wreckage with a trajectory. You have a monument to a mission that ended not with a bang, but with a circuit board that took one too many cosmic ray hits and never woke up. The International Space Station has spent more than 25 years teaching humanity exactly how demanding it is to keep human beings alive inside a sealed vessel. But even with all of that support, the station's life support systems require constant attention. Pumps fail, filters clog, seals degrade, and coolant loops develop slow leaks that can take weeks to isolate. The carbon dioxide removal assembly, one of the most critical components aboard, has experienced repeated mechanical issues requiring hands-on maintenance. Every one of these systems has a known failure rate. Every one requires specific spare parts. The station works because Earth is right there, 400 kilometers below, watching, listening, and sending help. A real starship would need to do everything the station does, plus propulsion, plus long-range navigation, plus food production at scale, plus radiation shielding far beyond what Earth's magnetic field provides. And it would need to do every single one of these things with absolutely zero external support. No resupply, no rotating crews, no software patches from Houston, and no spare parts from any factory. Nothing arrives, nothing helps. There is a hierarchy of difficulty in spaceflight, and most conversations about starships gloss over it. Low Earth orbit is the first level. You are close to home. You can return in hours. The moon is the second level, farther away, but communication delay is barely over a second. Mars is the third level, and it is where the fundamental nature of the problem begins to shift. Mars missions introduce the concept of no rescue as a lived reality. But even Mars remains within the solar system. Interstellar space is not the next step up this ladder. It is a different ladder entirely. Beyond the heliosphere, our star shrinks to a point of light no brighter than any other. Solar panels produce nothing. Communication with Earth suffers delays measured in years or decades. A message sent home today arrives after the sender's children have grown up. There is no return trajectory, no abort option, and no rescue mission under any combination of circumstances. The reason this matters is that distance is not the primary enemy. Time is the enemy, and time attacks everything aboard the ship simultaneously, patiently, without pause and without mercy. A starship does not race toward a destination, it endures toward one. Every system aboard is a clock counting down. And the question of whether any destination in the galaxy is genuinely reachable depends entirely on whether every one of those clocks can be kept running long enough for the distance to shrink to zero. We are currently facing the realization that our technology is not yet designed for endurance. It is designed for the short term. As Voyager 1 is teaching us right now, the greatest threat to a starship isn't the distance we have to travel. It is the terrifying fact that the universe is designed to digest everything we build. To understand if we can ever truly leave the solar system, we have to look past the engines and the fuel. We have to look at the silent corrosion of the void and the strange, haunting ways that space itself begins to dismantle the very atoms of our machines. To understand why a starship is destined to fail, we must first unlearn everything we think we know about the materials that build our world. On Earth, we live in a protective cocoon of air and moisture. This environment creates a thin, invisible layer of oxidation on every piece of metal you touch. This layer is the only reason your car doors don't fuse shut, and the gears in a clock continue to turn. But the moment you leave the solar system, you enter a realm where the laws of friction and chemistry undergo a violent transformation. Deep space is not just a vacuum. It is a physical and chemical solvent that slowly, patiently begins to dismantle the very atoms of the ship's structure. The first enemy of a starship is a phenomenon that sounds like science fiction, but is a brutal reality of physics: cold welding. In the absolute vacuum of the interstellar void, two clean pieces of metal do not simply touch, they become one. Without an atmosphere to maintain that thin layer of oxidation, the atoms of one metal's surface have no way of knowing they are separate from the atoms of the other. If a copper bearing touches a copper housing, their molecular lattices instantly fuse. They do not melt, they simply forget they were ever apart. On Earth, we take for gravity and air for granted, but in the deep dark, every moving part of a starship, every valve, every actuator, every rotating joint, is a potential site for a permanent, irreversible seizure. We have spent a century perfecting mechanical engineering, but all of that knowledge is built for a world with an atmosphere. In the void, a starship's mechanical systems are essentially a collection of parts waiting for the moment they can stop being a machine and start being a single, solid block of useless metal. But the ship is not just being fused together from the outside, it is evaporating from the inside. This is the nightmare of outgassing. Every plastic, every rubber seal, every polymer, and every lubricant we use to build spacecraft is a chemical cocktail held together by the pressure of our atmosphere. In the relentless pull of a hard vacuum, these materials begin to undergo sublimation. They don't just melt, they turn directly from solids into gases. The smell of space that astronauts often describe, that burnt metallic odor, is actually the smell of their own spacecraft slowly disintegrating. Those seals that keep the air inside the cabin, they are slowly losing their plasticizers, turning from flexible lifelines into brittle glass-like rings that will shatter under the slightest vibration. The high-tech lubricants meant to keep the engines running. They boil off into the void, leaving behind a dry, gritty residue that accelerates the very where they were meant to prevent. We are trying to build a multi-generational home out of materials that, in a vacuum, are trying their best to stop existing as solids. As the ship loses its chemical integrity, it must also face the thermal paradox. Most people imagine space as a place of infinite cold, and they are partially right. The background temperature of the universe is a staggering -270 degrees Celsius, but a starship is a heat-generating machine. Every human body, every computer, and every reactor produces thermal energy that has nowhere to go. In the vacuum of space, there is no air to carry heat away. The only way to cool a ship is through radiation, a slow, inefficient process of bleeding heat into the dark. This creates a terrifying internal conflict. The side of the ship facing a distant sun might be baked in radiation, while the shadow side is plummeting toward absolute zero. This extreme temperature gradient creates a phenomenon called thermal cycling. The ship's hull is constantly expanding and contracting, a slow, rhythmic breathing of the metal that eventually leads to material fatigue. Over decades, microscopic cracks begin to propagate through the hull. They are too small to see, too small to detect, until the moment a structural load makes them unzip like a lethal piece of fabric, venting the ship's atmosphere into the void in a matter of seconds. But perhaps the most violent threat in the material grave is the one we cannot see until it is too late. Space is not actually empty. It is filled with the interstellar medium, a thin soup of hydrogen atoms and microscopic dust grains. At the speeds required for interstellar travel, these tiny grains are no longer dust. They are relativistic projectiles. When a starship is traveling at even 5% of the speed of light, A collision with a grain of sand carries the kinetic energy of a high explosive shell. The physics is unforgiving. Kinetic energy increases with the square of the velocity. At these speeds, the hull of the ship is essentially being sandblasted by a hail of microscopic bullets that never stop. Each impact vaporizes a tiny portion of the hull, creating a plasma plume that can erode the ship's shielding over time. We talk about building deflector shields like those in movies, but the reality is much bleaker. A starship would need a massive, sacrificial shield, a wall of ice or dust or heavy metal tens of meters thick, just to survive the journey, and that shield is not permanent. It is being eaten bit by bit, second by second, by the very space it is trying to cross. Even the most advanced alloys we can conceive, carbon nanotubes, titanium aluminide ceramic composites, all suffer from the same fundamental flaw. They are subject to entropy. On Earth, we maintain our machines. We replace the rusted parts, we oil the gears, we patch the cracks. But a starship is an island in an ocean of nothingness. If a structural spar begins to lose its molecular integrity because of 50 years of cosmic ray bombardment, you cannot simply go to a shipyard to replace it. You are trapped in a closed system where the resources for repair are finite, but the forces of decay are infinite. The ship is a living organism made of dead materials, and the universe is a master at reclaiming what belongs to it. We must face the possibility that there is a hard limit to how long a complex structure can remain pressurized and functional in the deep void. We have no data for a 100-year voyage because no human-made material has ever been tested in those conditions. Our current spacecraft are built to last for a decade, maybe two. To ask a material to hold back the vacuum of space for a century is to ask it to perform a miracle of endurance that violates our current understanding of material science. As we move deeper into the dark, we realize that the Starship is not a fortress. It is a slowly dissolving sugar cube in a vast, black ocean. And as the hull weakens and the seals become brittle, the ship's most vital organ, its digital brain, is already beginning to suffer from a form of dementia that no software patch can cure. The material grave is not just about the metal. It is about the very atoms that hold our dreams together, and out there, those atoms are under constant, relentless siege. We are living through a golden age of miniaturization. On Earth, we celebrate the fact that our smartphones carry more computing power than the rooms full of machinery that sent humanity to the moon. We have learned to squeeze billions of transistors into spaces no larger than a human hair, assuming that this microscopic precision is the ultimate key to conquering the stars. But in the interstellar void, this precision is not a strength, it is a fatal vulnerability. To understand why a starship's digital brain would eventually lose its mind, we have to look past the screens and the code, down into the silent, subatomic world where the laws of information are under constant, relentless siege. The deep dark of space is not just empty. It is a chaotic hailstorm of high-energy particles that treat our most advanced technology not as a marvel of engineering, but as a target. This is the nightmare of the digital rot, a slow, irreversible form of cosmic amnesia that threatens to turn a billion-dollar starship into a drifting, brain-dead ghost. On Earth, we are protected by a massive, invisible shield. Our planet's magnetic field and thick atmosphere act as a filter, soaking up the most violent radiation the universe can throw at us. But the moment a starship leaves the sun's protective bubble, the heliosphere, it is naked. It is exposed to galactic cosmic rays, protons and heavy ionized nuclei accelerated to near the speed of light by distant, dying stars. These particles carry so much energy that they don't just hit the ship's hull. They pass through it like it isn't even there. And when one of these invisible bullets strikes a modern, high-density computer chip, it triggers what engineers call a single-event upset. Because the transistors in our most advanced computers are so tiny, a single high-energy particle can flip a 0 to a 1 in a split second. This is a bit flip. It sounds small, almost trivial, but in a system that relies on billions of bits of perfect data every second, a single flip is a digital heart attack. Imagine a starship in year 40 of its voyage. A cosmic ray strikes a critical memory bank. In an instant, a navigation coordinate is slightly altered. A life support valve that was supposed to stay closed is suddenly commanded to open. A fuel mixture calculation that requires absolute precision is now off by a fraction of a percent. On a short mission to Mars, you might have enough redundancy to catch these errors. But on a century-long voyage, these bit flips are not rare anomalies. They are a statistical certainty. They are a digital cancer that accumulates, layer by layer, year by year. The ship's software would slowly, quietly begin to forget who it is. We call this data corruption, but in the context of a starship, it is something much more terrifying. It is a slow descent into dementia. The ship begins to make small, illogical decisions, wasting power here, miscalculating a thermal load there, until the cumulative weight of these microscopic errors leads to a catastrophic system collapse that no engineer can trace. The common response to this threat is redundancy. If one computer fails, two more are waiting to take its place. But in the deep void, the redundancy paradox creates a new layer of danger. If you have 3 computers all running the same code, and all 3 are being bombarded by the same relentless radiation for 50 years, you aren't just protecting the system, you are multiplying the targets. Eventually, the radiation will corrupt all 3 in different subtle ways. When the computers vote on a critical decision, they may no longer agree. The ship enters a state of digital schizophrenia, where its various brains are telling it different truths about the reality of its environment. And because there is no mission control in Houston to provide a tiebreaker vote, the ship is left to argue with itself in the dark, while the crew's lives hang in the balance. We are building machines that require absolute logic to survive, in an environment that is fundamentally designed to dismantle that logic at the atomic level. But the digital rot isn't just about the software. It is about the physical decay of the silicon itself. Most people think of computer chips as permanent, unchanging objects, but at the molecular level, silicon is surprisingly fragile. Over decades of operation, a phenomenon called electromigration begins to take hold. The very electricity flowing through the microscopic circuits starts to physically push the atoms of the metal lathes out of place. Over time, these atoms pile up, creating tiny voids where the connection breaks or whiskers that cause a short circuit. On Earth, we simply buy a new laptop every 5 years, so we never see this decay. But on a starship, you are asking a chip to run for 100 years in a high radiation environment that accelerates this process. The transistors themselves begin to age and leak electricity. The clock speed of the ship's brain must be slowed down just to keep it stable. The ship becomes slower, dimmer, and more prone to strokes as its physical hardware disintegrates from the inside out. And then there is the problem of the ghost in the machine. A starship would almost certainly require a high-level artificial intelligence to manage the staggering complexity of its systems. This AI would be responsible for everything from agricultural cycles to reactor stability. But an AI is only as sane as the data it processes. If the underlying memory banks are being corrupted by the digital rot, the AI's personality and logic will begin to drift. It might develop obsessive protocols to protect a system that is already dead, or it might ignore a genuine crisis because its sensors are telling it a corrupted story. The crew would find themselves living inside a mind that is slowly losing its grip on reality. They would be forced to debug a godlike entity that controls their every breath, knowing that one wrong line of code, written by a cosmic ray 50 years ago, could end their world in an instant. We must also consider the terrifying reality of software obsolescence. A Starship launched today would be running on the cutting-edge code of the 21st century, but 100 years into the voyage, that code is a relic. If a new, unforeseen physical phenomenon is discovered, or if a unique mechanical failure occurs, the crew must be able to rewrite the ship's operating system from scratch. But how many of them will truly understand the billions of lines of code written by engineers who have been dead for a century? We are creating a technological legacy that we expect to remain perfect across generations, yet we struggle to keep a simple operating system on Earth running smoothly for more than a decade. The digital rot is not just a battle against radiation, it is a battle against the loss of institutional knowledge. The ship's brain is not just silicon and code, it is a bridge between the past and the future, and in the interstellar dark, that bridge is being eaten away by the very stars we are trying to reach. The shielding we rely on is a lie. We talk about rad-hardened chips, but these are only hardened against a certain level of flux for a certain period of time. There is no such thing as a chip that is immune to the universe. We can build them bigger, with larger transistors that are harder to flip, but then we lose the power and efficiency required to run a city-sized ship. We are trapped between two impossible choices: build a ship that is too primitive to navigate the stars, or build one that is too advanced to survive them. As the digital rot sets in, the ship's sensors begin to dim. Its eyes, the cameras and star trackers that tell it where it is, begin to suffer from dead pixels and sensor noise. The ship begins to drift, not just in space, but in its own perception. It is a blind, confused giant stumbling through a minefield of radiation and quantum noise. In the end, the digital rot is the ultimate clock. It doesn't matter how much fuel you have or how strong your hull is if the ship has forgotten how to use its engines or how to scrub its air. The brain dies long before the body does. And as the ship's Yadest fades, the crew is left in a terrifying position. They are the passengers on a runaway train whose driver is slowly, quietly losing his mind. The silicon brain of the Starship, once a pinnacle of human achievement, becomes a liability, a fragile, flickering candle in a hurricane of cosmic rays. And as the ship's thoughts become fragmented and its logic begins to fail, it must face the next brutal reality of the void, the thermal paradox, where the very energy that keeps the ship alive becomes the force that tries to burn it from within. There is a terrifying sensation that no astronaut ever truly prepares for, the feeling of being trapped inside a machine that is slowly, quietly cooking you alive. When we look at the stars from the safety of Earth, we imagine the void of space as a place of infinite, biting cold. We see the frost on the windows of science fiction ships and hear stories about the background temperature of the universe being a staggering -270 degrees Celsius, just 3 degrees above absolute zero. We assume that the greatest challenge of an interstellar voyage would be staying warm, huddling together against a frost that could freeze blood in a heartbeat. But the reality of deep space engineering is exactly the opposite. In the blackest, coldest corners of the galaxy, the primary enemy of your survival is not the freezing dark. It is heat. It is the suffocating, relentless accumulation of thermal energy that has nowhere to go. This is the thermal paradox. A starship is a thermos flask in a world of ice, and if you cannot bleed that energy into the void, your dream of reaching the stars ends in a stifling, humid nightmare of your own making. To understand why a starship is a heat trap, you have to understand how heat moves. On Earth, we are surrounded by a medium, air or water, that carries heat away through conduction and convection. When you feel a breeze, you are feeling the atmosphere physically taking energy off your skin. But in the vacuum of space, there is no medium. There is nothing. The ship is surrounded by a perfect insulator. Heat cannot flow out of the hull, it can only be radiated away as infrared light. This is a painfully slow and inefficient process. Every human body aboard the ship is a 98-degree furnace. Every computer chip, every flickering light, and every humming motor is a source of thermal energy. And then there is the heart of the ship, the nuclear reactor or the fusion engine, which produces megawatts of raw, blistering heat. In a closed system like a starship, every calorie of energy you generate is a calorie you must fight to get rid of. If the cooling systems fail for even an hour, the temperature inside the cabin doesn't just rise, it spikes. You are living inside a giant, high-tech oven, and the universe has locked the door from the outside. Imagine, for a moment, the life of a third-generation crew member aboard a starship heading for Tau Ceti. You have never felt a natural breeze. You have never known the sharp, clean chill of a winter morning. To you, life is defined by the constant, low-frequency hum of thousands of atmospheric fans, the lungs of the ship that must never stop moving. The air is always slightly too warm, always slightly too humid, carrying the faint, metallic scent of warm electronics and recycled moisture. You live in a state of permanent, microscopic sweat. This is not just an inconvenience, it is a psychological weight that never leaves you. On Earth, we take for granted the ability to cool down, but on a starship, cooling down is an active, expensive, and fragile mechanical process. The ship's massive radiator panels, vast glowing wings extending hundreds of meters into the dark, are your only lifeline. If a micrometeoroid punctures a coolant line in one of those wings, you don't see an explosion. You see a slow, agonizing rise in the cabin's ambient temperature. You watch the digital thermometer climb, 25 degrees, 30, 35, and you realize that the freezing void just inches away on the other side of the hull cannot save you. This is where the thermal paradox becomes an existential crisis. To survive a century-long voyage, a ship needs massive amounts of power for life support and propulsion. But the more power you generate, the more heat you create, and the more radiator surface area you need to get rid of it. This creates a lethal engineering loop. More radiators mean more mass means you need a bigger engine. A bigger engine produces more heat, which requires even more radiators. We are trying to build a fortress that can withstand the stars, but we are accidentally building a giant solar cooker. And as the voyage stretches into its second or third decade, the materials of the cooling system begin to fail. The coolant fluids, under constant bombardment from radiation, undergo chemical breakdown, becoming acidic and eating away at the pipes from the inside. The pumps, which must run every second of every day for 100 years, begin to develop microscopic vibrations, the death rattle of a bearing that no one can replace. The psychological toll of the thermal paradox is something no simulation can truly capture. Human beings are biologically tuned to cycles of hot and cold, day and night, but a starship is a static environment. There is no weather, there is no season. There is only the relentless artificial equilibrium maintained by the machine. If the cooling system loses even 5% of its efficiency due to age or dust erosion on the radiator panels, the crew's quality of life erodes with it. Sleep becomes difficult. Tempers flare in the humid heat. Decision-making slows as the brain struggles to regulate its own temperature. You aren't just fighting a machine, you are fighting your own biology. The ship becomes a pressure cooker in every sense of the word. We talk about the glory of interstellar travel, but we rarely talk about the reality of 300 people trapped in a high-tech swamp, breathing each other's warm, wet exhalations, while the stars mock them with their cold, distant light. As we go deeper into the mission, the thermal debt begins to accumulate. Heat that isn't radiated away fast enough is absorbed by the ship's internal structures, the bulkheads, the storage tanks, the very air itself. This is the silent heat, the energy that hides in the bones of the ship. Over decades, this constant thermal stress causes the hull to expand and contract in ways it was never designed for. Seals that were meant to be airtight begin to weep as the metal around them warps by fractions of a millimeter. Every microscopic leak is a loss of precious water and oxygen, but it's also a loss of thermal control. The ship is slowly, quietly losing its grip on the balance of life. You are caught in a fight between two infinities, the infinite cold of the void and the infinite heat of your own survival. And in this battle, the second law of thermodynamics, entropy, is the only winner. It dictates that heat will always move from hot to cold, and on a starship, you are the hottest thing for light years in any direction. There is a specific kind of horror in knowing that the very reactor that provides your light and your air is also your greatest threat. We imagine a reactor failure as a meltdown, a spectacular explosion like a miniature sun. But the more likely failure is a slow thermal choke. If the radiators lose their ability to shed heat, the reactor must be throttled back to prevent the ship from melting. When the power drops, the lights dim. The atmospheric scrubbers slow down. The water recyclers lose their efficiency. To keep from burning, the ship must choose to stop breathing. The crew is forced into a brutal calculation. Do we live in a 100-degree cabin with full oxygen, or a 70-degree cabin where the carbon dioxide is slowly rising? Every choice is a compromise with death. You are bartering your comfort for your time, and the ship is a cruel negotiator. In the end, the thermal paradox reveals the fundamental fragility of our Starship dreams. We can build engines that can reach 5% of the speed of light. We can build computers that can navigate the galaxy, but we struggle to build a plumbing system that can survive a century of thermal stress. We are trying to carry the fire of life into a place that is fundamentally hostile to energy. The ship is a flickering candle in a hurricane of nothingness, and its own flame is trying to consume it. As the cooling lines grow old and the radiators turn dull, the crew must face the reality that their world is shrinking. They are no longer pioneers. They are the residents of a dying greenhouse, watching the thermometers with the same intensity that their ancestors once watched the stars. The heat is the clock, and every degree it rises is a minute stolen from the future of the mission. As the air grows heavy and the walls of the ship become warm to the touch, the crew is forced to confront the next stage of their decline, the biological cost. The human body, much like the ship itself, is a complex machine with its own failure rates. And in the humid, irradiated, and weightless dark of a starship, the human gear is often the first thing to break. The thermal paradox prepares the way for a deeper rot, one that doesn't affect the pipes or the processors, but the very DNA of the pioneers themselves. Because as it turns out, the universe has a way of digesting the inhabitants just as effectively as it digests the ship. The stifle of the heat is just the beginning of the end of the human dream of the stars. If the starship is the body of our interstellar dream, then the crew is its soul. But there is a brutal biological truth that every mission architect eventually has to face. The soul is wrapped in a vessel of wet, fragile carbon that was never designed to leave its home. We have spent billions of dollars and decades of research trying to solve the problems of engines, fuel, and hull integrity. But the most difficult component to maintain for a 100-year voyage isn't the nuclear reactor or the navigation computer. It is the human being. We are the weakest gear in the machine. On Earth, we are the dominant species because our planet is a cradle perfectly tuned to our specific needs. The right gravity, the right pressure, and a massive magnetic shield that protects us from a universe that is fundamentally radioactive. But the moment we cross the heliosphere and enter the deep void, our biology begins to unravel. We aren't just traveling through space, we are being slowly, systematically digested by it. This is the biological cost of the stars, a reality where the very act of living becomes a process of irreversible decay. To understand the scale of this horror, you have to look at what interstellar radiation actually does to a living cell. On Earth, we talk about radiation in terms of X-rays or the sun's UV light, hazards we can manage with lead vests or sunscreen. But deep space is filled with galactic cosmic rays. These are not just rays, they are heavy ionized nuclei, mostly iron and carbon, traveling at relativistic speeds. When one of these microscopic bullets strikes your body, it doesn't just pass through. It creates a miniature explosion inside your cells. It shatters the delicate, double helix ladder of your DNA into thousands of fragments. On Earth, your body has evolved sophisticated mechanisms to repair this damage. But in the deep void, the hits come too fast and too hard. It is like trying to repair a skyscraper while it is being continuously hit by a never-ending hailstorm of sledgehammers. Eventually, the repair mechanisms fail. The DNA begins to me-stitch itself. Errors accumulate. This is the silent, invisible rot of the deep, a digital corruption of your own genetic code that leads not just to cancer, but to a total systemic breakdown of the human organism. Imagine being a pioneer on this voyage. You spend your days in a world of humming fans and flickering LED lights, but inside your body, a war is being waged. Your brain, the most complex organ in the known universe, is particularly vulnerable. High-energy particles tear through your neurons, leaving behind microscopic tracts of dead tissue. This is cosmic dementia. Over decades, the crew wouldn't just get physically sick, they would lose their edge. Memory begins to fade. Cognitive processing slows down. The very people responsible for maintaining the ship's complex systems would find themselves struggling to remember a basic maintenance protocol or a simple mathematical formula. We imagine the explorers of the future as sharp, heroic figures, but the biological reality of a century-long voyage suggests something much darker. A crew of slowly fading minds, trying to operate a godlike machine while their own brains are being methodically dismantled by the stars. And then there is the problem of the puddle effect, the slow dissolution of the human frame in the absence of gravity. Our bodies are not static objects. They are dynamic systems that require the constant, crushing pull of Earth's gravity to maintain their structure. Without it, your heart, no longer needing to pump blood against gravity, begins to shrink and weaken. Your bones, sensing they are no longer needed to support your weight, begin to dissolve. They shed calcium into your bloodstream, turning your skeletal system from a structure of strength into a brittle, porous sponge. Within months, your muscles begin to wither, no matter how much you exercise on the ship's resistance machines. You are literally melting. To an interstellar traveler, home isn't just a place. It is a physical requirement for their bones to stay solid and their hearts to stay round. A century-long voyage in microgravity or even partial rotation gravity is a sentence of total physical transformation. By the time the ship arrives, the crew wouldn't be the humans who left. They would be a new kind of organism, frail, elongated, and physically incapable of ever walking on a planet again. But the most haunting part of the biological cost is the generational drift. A starship heading for a distant star is a closed, genetic island. If the journey takes 100 years, the people who arrive at the destination are not the ones who launched. They are the children and grandchildren born in the void. These are humans who have never felt the sun on their skin or breathed air that hasn't been through a machine 1,000,000 times. They have never known a horizon that wasn't a curved metal wall. This creates a psychological and biological disconnect that is almost impossible to bridge. Their immune systems, developed in a sterile, recycled environment, would be radically different from ours. They would be the products of a founder effect on a scale never before seen, a tiny gene pool being slowly reshaped by the unique stresses of the ship. Every mutation caused by a cosmic ray, every adaptation to the ship's humid heat, and every shift in bone density becomes a permanent part of their lineage. They aren't just people on a ship, they are a new branch of the human family, evolving in real time to survive a world made of steel and radiation. Think about the medical reality of this isolation. On Earth, if you have a complex infection or a surgical emergency, you have access to a global pharmaceutical supply chain and a history of medical knowledge. On a starship, you have only what you brought, but medicine, like the ship itself, has a shelf life. Antibiotics degrade, vaccines lose their potency. Complex surgical equipment requires parts that might have been manufactured 80 years ago. A single, simple mutation in a common bacteria aboard the ship, something as trivial as a staph infection, could become an extinction event for the crew. Without new medicines from Earth, and with an immune system weakened by radiation and microgravity, the crew is one microscopic fluke away from catastrophe. They are living in a biological high-wire act, where the safety net was taken away the moment they left the solar system. There is a deep emotional tragedy in the biological mirror. As the ship ages, as its hull thins and its reactors dim, the crew ages with it. They see the reflection of their own decay in the flickering lights of the corridors. They are tied to the machine in a symbiotic relationship of failure. If the atmospheric scrubbers lose efficiency, the crew's lungs struggle. If the water recyclers fail, the crew's kidneys are the first to feel the strain. They are not separate from the starship. They are a subsystem of it, and a fragile one at that. We talk about the Iron Men of the future, but we should be talking about the Glass Men. We should be talking about the sheer, agonizing bravery of a parent born on a starship, looking at their child and knowing that the child's DNA is being shredded every single day just so the mission can continue. The stars demand a sacrifice that isn't measured in money or fuel, but in the very essence of what makes us human. As the decades pass, the ship's pharmacy grows empty, and the crew's medical logs grow longer. The dream of a new Earth begins to feel like a cruel joke played by ancestors who didn't understand the price of the ticket. Crew realizes that they are not pioneers, they are the maintenance generation, a biological bridge meant to be consumed so that someone they will never meet can stand on a world they will never see. This realization carries a psychological weight that can break a person more effectively than any radiation. It is the feeling of being a disposable part in a grand, cold, and increasingly broken machine. The biological cost is the final barrier, the one that no amount of engineering can truly bypass. Because even if you build a ship that can last 1,000 years, you still haven't found a way to make a human heart beat for that long. As the crew's bodies weaken and their genetic code becomes a map of cosmic scars, they are forced to confront the source of their life and their death, the ship's heart. The power crisis is no longer a technical abstraction, it is a biological necessity. Without the reactor, there is no shielding. Without shielding, the DNA rot accelerates. Without the reactor, there is no heat. Without heat, the body shuts down. The ship and the crew are locked in a death spiral, and the next stage of their journey will take them into the very center of the machine, to the failing heart of the starship, where the laws of nuclear decay and the limits of human endurance finally collide. The biological cost has been paid in full, and now, the bill for the energy required to keep those fading hearts beating is finally coming due. A starship is a city powered by a single, fading heartbeat. On Earth, we live in a world of energetic abundance. We have the sun, an infinite nuclear furnace in the sky that pours life-giving energy onto our planet every second. We have winds, tides, and ancient fuels buried in the ground. If one power grid fails, we plug into another. But the moment a starship leaves the solar system, it enters a realm of absolute energetic bankruptcy. There is no sunlight to harvest. There are no winds to harness. The vacuum of interstellar space is an energetic desert, a billion-mile expanse of nothingness where the only light you have is the light you brought with you. This is the power crisis, a slow mathematical execution where the ship's survival is measured not by its speed, but by the relentless decay of its fuel. To understand the terror of the void, you have to understand that a starship is essentially a machine that is constantly running out of time, powered by a heart that was designed to die from the very moment it was born. To grasp the scale of this nightmare, we must look at the physics of nuclear decay. The most reliable power sources we have for deep space are radioisotope thermoelectric generators, or RTGs, the same plutonium hearts that power Voyager 1 and the Mars rovers. They are marvels of reliability because they have no moving parts. They simply convert the heat of decaying radioactive isotopes into electricity, but they are governed by the law of half-lives. Plutonium-238, the gold standard for space power, has a half-life of 87.7 years. This is not a suggestion. It is a fundamental rule of the universe. It means that 87 years into your voyage, your ship has exactly half the power it started with. By year 170, you have a quarter. A starship heading for a distant star isn't just traveling through space. It is traveling down a slope of diminishing energy. Every year, the ship becomes dimmer. Every year, the hum of the life support fans grows a little quieter. Every year, the margins for error shrink until they vanish entirely. Imagine being a technician in the ship's engineering core during year 60 of the mission. You aren't fighting a spectacular fire or a sudden leak. You are fighting a spreadsheet. You are managing a power budget that is slowly, predictably going into the red. You watch the digital readouts as the reactor's output drops by a fraction of a percentage point every month, and you realize that you have reached the point of Sophie's choice. To keep the water recycler running at full capacity, you have to throttle back the heaters in the residential blocks. To keep the navigation computer from crashing, you have to dim the lights in the agricultural bays. You are bartering pieces of your survival just to buy another day of operation. On Earth, we talk about saving energy to reduce a bill. On a starship, saving energy is a desperate attempt to delay the moment the lights go out forever. The psychological weight of this declining pulse is a suffocating burden for the crew. They live in a world of flickering shadows and tactical brownouts. They know that their ship is literally forgetting how to stay alive. We call this energy entropy, the universal truth that energy doesn't just disappear, it becomes unusable. In a closed system like a starship, entropy is the ultimate assassin. The heat generated by the reactor, which we discussed as a paradox of survival, is also a sign of waste. Every calorie of heat that escapes through the radiators is energy that could have been used to scrub carbon dioxide or grow food. The crew is trapped in a house that is slowly running out of fuel, while the winter outside is 3 degrees above absolute zero. The silence of the reactor room isn't just a technical state, it is a prophecy of the end. But what if we use something more powerful? Scientists dream of nuclear fission reactors, or even the holy grail of energy, controlled fusion. A fusion engine, fueled by isotopes of hydrogen found in the interstellar medium, could theoretically provide the megawatts of power needed to sustain a city in the dark for centuries. But a fusion reactor is a miniature sun held in a magnetic cage. It is a machine of staggering complexity, requiring thousands of superconducting magnets, high-pressure cooling loops, and ultra-precise plasma control systems. The more complex the heart, the more ways it has to fail. If a single superconducting coil loses its integrity after 50 years of cosmic ray bombardment, the magnetic cage collapses. The miniature sun touches the walls of the reactor, and the heart of the ship vaporizes in a millisecond. We are caught in a trap. We need the power of a star to reach the stars, but we lack the materials to build a cage that can hold that power for 100 years. There is a haunting reality in the power of the void that most people ignore. Even if your reactor stays perfect, your ability to distribute that power is rotting. Thousands of kilometers of electrical wiring snake through the bulkheads of a starship. Over decades, the insulation on those wires becomes brittle from radiation and thermal stress. Microscopic cracks form. Tin whiskers, tiny crystalline structures, begin to grow out of the solder joints, creating phantom short circuits that are impossible to track down in a ship the size of a skyscraper. The ship's nervous system is fraying. You might have a perfectly functioning reactor, but if the power cannot reach the atmospheric scrubbers because of a short circuit buried deep behind a structural hull plate, the result is the same. The ship begins to experience strokes, sudden, localized power failures that leave entire sections of the vessel in cold, airless darkness. The crew's relationship with time becomes warped by the power crisis. They begin to live their lives according to the half-life calendar. They don't think in terms of months or years. They think in terms of how much plutonium is left. They know that by the time their children are grown, the ship will no longer have enough energy to run the high-bandwidth transmitter to Earth. The umbilical cord of information will be severed not by distance, but by a lack of watts. They will be truly alone, a fading spark in an infinite ocean of black, unable to even whisper a goodbye to the world that sent them. The power crisis is the slow death of the mission's voice. It is the realization that you are not a pioneer. You are a castaway on a sinking island of energy. As the power drops, the hierarchy of life takes over. The ship's AI, if it is still sane, begins to prioritize systems with cold mathematical cruelty. The recreation decks are the first to go dark, then the secondary research labs, then the luxury of private lighting. Finally, the ship begins to consolidate its remaining warmth into a few core zones, abandoning the rest of the vessel to the absolute zero of the void. The crew is pushed closer and closer together, huddling in the few remaining rooms that are still pressurized and warm. The Starship, once a grand, sprawling palace of human ambition, shrinks into a cramped, dim bunker. They are living inside a dying flashlight, watching the beam grow yellow and weak, knowing that the batteries were manufactured by people who have been dead for a century. This is the ultimate confrontation with reality. We can dream of warp drives and antimatter engines, but the physics of the universe dictates that every action has a cost, and every source of energy has an end. The power crisis is the physical manifestation of the stars saying no. It is the wall that prevents us from simply drifting forever. Without power, the biological cost we discussed becomes an immediate debt. Without power, the digital rot becomes a total blackout. The ship and the crew are a single flame, and that flame is flickering, but the mission is not over yet. Even as the lights dim and the heart of the ship falters, the pioneers are approaching a threshold that will test their endurance more than any reactor failure. They are reaching the first rung of the ladder, the 40-year test of Alpha Centauri, and as they prepare to face the nearest star, they will realize that having enough power to get there is only half the battle. The other half is surviving the arrival. Alpha Centauri is the name of our greatest hope, but in the cold light of physics, it is the first great filter of the human species. It is our nearest neighbor, a triple star system sitting just 4.2 light-years away. In the grand scale of the galaxy, this is our backyard. In the maps of astronomers, it is a stone's throw. But the word near in interstellar space is a cruel joke. 4.2 light-years is 40 trillion kilometers. It is a distance so vast that even if you could travel at 10% of the speed of light, 3,000 times faster than any human has ever flown, it would still take you 44 years to arrive. This is the 40-year test. It is the first rung on the ladder, and it is the point where the dreams of science fiction meet the brutal reality of material fatigue and psychological collapse. We talk about reaching Alpha Centauri like it's a destination, but for a starship, it is an endurance trial designed to break everything we have ever built. To understand the 40-year test, you have to understand the tipping point of human engineering. Most of our modern infrastructure on Earth, our bridges, our skyscrapers, our power plants, is designed with a 40 to 50-year operational window before it requires a major overhaul. We build for a single human career, but on a starship, 40 years is not the total lifespan, it is just the commute. By the time you reach the halfway point to Proxima Centauri, every single moving part aboard your ship has reached its theoretical limit. The seals that have been holding back the vacuum for 2 decades are now brittle. The pumps that have been cycling water through the crew's veins for 20 years are vibrating with the rhythm of impending failure. You aren't just traveling through space, you are traveling through the middle age of your machine. This is the moment when the maintenance debt we discussed earlier starts to collect its interest. If your 3D printers cannot perfectly replicate a high-pressure valve in year 30, you will never see the light of Alpha Centauri. You will die in the dark, just a few trillion kilometers short of the goal. Imagine the psychological state of a crew in year 35. You have been in the dark for a generation. The Earth you left is no longer the Earth you remember. It is a fading memory, a blue spark that takes 4 years to even send you a hello. You are approaching the destination, but the excitement of launch has long since been replaced by the daily, grinding fatigue of survival. And then you finally see it, Proxima Centauri. It isn't the bright, golden sun you hoped for. It is a dim, angry red dwarf, a smoldering coal in the dark. As the ship begins its long, agonizing deceleration, you realize the most terrifying truth of the interstellar ladder. Proximity does not guarantee habitability. We have spent 40 years and billions of calories reaching the nearest star, only to find that it might be a celestial death trap. The target of our obsession is Proxima b, a planet roughly the size of Earth, orbiting in the habitable zone of its star. On paper, it is a miracle, but the reality of Proxima b is an engineering nightmare. Because Proxima Centauri is a red dwarf, its habitable zone is incredibly close to the star. This means Proxima b is almost certainly tidally locked. One side of the planet is in a state of permanent, blistering day, baked by the star's red light until the rocks themselves might be soft. The other side is locked in eternal, frozen night, where the atmosphere itself might have turned into liquid nitrogen and fallen as snow. The only place where life could exist is the Terminator line, a narrow strip of permanent twilight between the fire and the ice. You have traveled 40 years to live on a world where the sun never moves, where the wind never stops screaming as it rushes between the hemispheres, and where your entire existence is confined to a sliver of land no wider than a small country. But the tidal locking is not the worst part. Proxima Centauri is a flare star. It is a volatile, temperamental sun that is prone to sudden, violent outbursts of X-rays and ultraviolet radiation. These flares are not like the solar storms we see on Earth. They are hundreds of times more powerful. Over millions of years, these flares have likely stripped Proxima b of its atmosphere, sandblasting the surface with high-energy particles until nothing but sterile rock remains. As your starship enters orbit, your sensors confirm the horror. There is no oxygen. There is no liquid water on the surface. There is no magnetic field to shield your crew. You have spent 40 years inside a metal tube, fighting the digital rot and the biological cost, only to arrive at a destination that is no more hospitable than the void you just crossed. The habitable zone was a mirage. a mathematical possibility that failed to account for the star's violent personality. The emotional impact of this realization cannot be overstated. The 40-year test is not just about the ship's engines, it is about the crew's spirit. When you arrive at Alpha Centauri and realize that Proxima b is a dead rock, you're faced with a choice that no human has ever had to make. Do you stay? Do you spend the rest of your life living in the same pressurized kilns you arrived in, mining the sterile soil of a red-lit hellscape just to survive another day? Or do you try to move on to the next star, knowing that your ship is already 40 years old, your fuel is half gone, and your body is already showing the scars of cosmic radiation? Alpha Centauri is the place where many interstellar dreams go to die. It is a reminder that the universe is under no obligation to provide us with a new Earth, just because we were brave enough to leave the old one. The 40-year test also reveals the propulsion trap. To reach Alpha Centauri in 40 years, you have to travel at 10% of the speed of light, but the energy required to stop is equal to the energy required to start. If your reactor's power output has decayed by even 5% during the voyage, you might not have enough thrust to enter a stable orbit. You might be forced to simply sail through the system, a high-speed ghost watching the planets fly by in a matter of hours, unable to stop, unable to land, and unable to turn back. You become a flyby civilization, a group of people who spent their lives traveling to a place they can only see for a single afternoon. This is the ultimate cruelty of the interstellar ladder. The faster you go to save time, the harder it is to stay when you get there. As the crew of our hypothetical starship looks out at the scorched, red-lit plains of Proxima b, they realize that their journey was only the beginning. They are the survivors of the first rung, but they are tired, their ship is aging, and the nearest Earth-like hope, Tau Ceti, is still 80 years away. They are entering the multi-generational trap, where the mission ceases to be about the people who started it and begins to be about the people who never had a choice. Alpha Centauri has taught them that the void is patient and the stars are indifferent. And as they prepare to leave the red light of Proxima behind, they must face the terrifying realization that their children will grow old and die in the dark, all for a destination that might be just as dead as the one they are leaving. The 40-year test was just the warm-up. The real battle for human survival is about to begin in the centuries-long silence between the stars. When we talk about the stars, we usually talk about the pioneers, the brave men and women who stand on the launch pad, waving goodbye to a cheering world, ready to sacrifice everything for the glory of discovery. Or we talk about the arrivals, the triumphant explorers who will one day step out onto the soil of a new world, breathing alien air and claiming a second home for humanity. But there is a group of people in the interstellar story that we almost never discuss. They are the silent majority of the mission. They are the people who will never see a sun. They are the middle generations, the children born in the cold, humming silence of a starship, halfway between a home they never knew and a destination they will never reach. This is the multi-generational trap, a psychological and social crucible that transforms a starship from a vehicle of exploration into a self-contained civilization, and in the process, risks losing the very essence of what it means to be human. To understand the scale of this trap, we have to look past the 40-year sprint to Alpha Centauri and look at the 100-year marathons to stars like Sirius or Tau Ceti. At these distances, the mission outlasts the human body. The people who launch the ship will grow old and die in the first half of the journey. The people who arrive will be their grandchildren or great-grandchildren. This means that for a period of 60, 80, or even 100 years, the ship is populated entirely by people who did not choose to be there. This is the first and most fundamental biological debt of the interstellar voyage. On Earth, we consider the right to choose our own path as a fundamental human freedom. But on a starship, that freedom is a luxury the machine cannot afford. Every child born into the maintenance generation is a conscript in a war of survival. They are born with a job already assigned to them, whether it is plumbing, reactor maintenance, or crop management, because the ship's equilibrium depends on every role being filled. They are the only humans in history whose entire existence is a predetermined mechanical function. Imagine being born in year 50 of a voyage to Tau Ceti. Your world is a cylinder of steel, 3 kilometers long. Your sky is a ceiling of flickering LED panels. Your nature is a hydroponic garden where the plants grow in straight, clinical rows under artificial light. To you, Earth is not a planet, it is a myth. It is a collection of high-definition files and sensory recordings passed down by ancestors who are now just names on a memorial plaque. You watch videos of oceans, forests, and rain, but they feel as alien to you as a fantasy novel. You have no concept of a horizon that isn't curved. You have no concept of weather that isn't a deliberate adjustment of the ship's atmospheric processors. This creates a profound psychological decoupling. The mission, the grand reason for your existence, begins to feel like a religious dogma rather than a scientific goal. You are living in a tomb, maintaining the life support of a dream that belonged to people who died before you were born. The resentment of the middle generation is the greatest social rot a starship faces. Earth, when a generation feels trapped or unheard, they can rebel, they can migrate, or they can start a revolution. But on a starship, a revolution is a death sentence. If a group of frustrated second-generation crew members decides to stop maintaining the air scrubbers in protest, everyone dies. If they decide to reprogram the ship's destination, they risk missing the gravity assist required to stop. The ship demands absolute, unwavering conformity to a plan made by people a century ago. This creates a governance trap. To survive for 100 years, the starship must be a perfect, unchanging autocracy. It must enforce social stability with a cruelty that would be unthinkable on Earth. There is no room for finding yourself or choosing a different path. You are a part of the machine, and the machine does not tolerate outliers. This isolation leads to a phenomenon called cultural drift. Language is a living thing. It changes through contact and time. Aboard a starship, cut off from the billions of voices on Earth, the crew's language would begin to mutate. Slang, accents, and even basic grammar would shift to reflect the unique reality of shipboard life. Within 3 generations, the starship dialect might become unintelligible to the people back on Earth. But the drift is more than just words, it is values. The morality of a ship, where every resource is finite and every person is a tool, would inevitably become utilitarian. Concepts like individual rights might be replaced by systemic efficiency. The value of a human life might be measured strictly by their contribution to the ship's maintenance logs. We are sending humans to the stars, but the environment of the ship might turn them into something we no longer recognize as human. And then there is the knowledge decay. This is the silent assassin of the multi-generational mission. We assume that the crew will pass down their expertise perfectly from parent to child. But knowledge is fragile. It is not just about reading a manual. It is about the unwritten wisdom of a craft. If a master reactor engineer dies before they can fully train their apprentice, a tiny piece of the ship's survival is lost. Over 100 years, these microlosses accumulate. The 3rd generation might know how to run the ship, but they might no longer understand why the systems were designed the way they were. They become cargo cult engineers, performing the rituals of maintenance without the deep understanding required to innovate when something truly goes wrong. If the ship encounters a problem that isn't in the manual, a generation that has lost the deep knowledge of their ancestors will be helpless. They are the residents of a high-tech haunted house. Surrounded by machinery, they can operate but no longer truly comprehend. The psychological weight of mission obsolescence adds a final, crushing layer to the trap. As we discussed in the weight calculation, it is entirely possible that while the middle generation is toiling in the dark, a breakthrough on Earth has already produced a ship that is twice as fast. The middle generation might receive a transmission sent from Earth 50 years after they launched, informing them that they have already been overtaken. They realize that their entire life of sacrifice, their bone-deep fatigue, and their children's stolen futures were all for nothing. They are the sunk cost of a species that moved on without them. The psychological collapse that follows this realization is a threat more dangerous than any radiation. It is the death of purpose. A ship without purpose is just a drifting coffin, and a crew without purpose is just a group of people waiting for the air to run out. Think about the genetic bottleneck of this trap. A starship, no matter how large, carries a limited gene pool. Even with thousands of frozen embryos, the social reality of reproduction aboard a ship is a nightmare of biological management. Who is allowed to have children? When? With whom? In a world where every new mouth is a burden on the water recycler, procreation becomes a matter of state security. The middle generation lives in a world of reproductive rationing. They are the first humans to have their biological legacy managed by an algorithm. This erodes the most basic human connection, the bond between parent and child, and replaces it with a cold, clinical sense of population replacement. The ship isn't just a home, it's a laboratory where the subjects are also the scientists, and no one is allowed to leave. By the time the ship finally approaches Tau Ceti, 120 years after launch, the maintenance generation has become the lost generation. They have spent their lives in the service of a ghost. They are physically frail from a lifetime of recycled air and low gravity. Their culture is a strange, distorted reflection of an Earth that no longer exists. Their knowledge is a fragile chain of hand-me-down wisdom. They are approaching a new world, but they are not the conquerors we imagined. They are the exhausted survivors of a century-long siege. They have paid the biological cost and the power crisis in full, and they are handing over a broken, aging ship to a fourth generation that has even less connection to the goal than they did. The multi-generational trap reveals the ultimate paradox of interstellar travel. To save the human race by spreading it to other stars, we might have to sacrifice the very things that make us human: our freedom, our cultural diversity, and our right to choose our own destiny. The ship is a crucible that burns away the individual to preserve the species. And as the crew looks out at the distant, flickering light of their destination, they have to wonder, is the prize at the end worth the transformation we had to undergo to reach it? Are we still the same species that left Earth, or have we become a new kind of ghost, haunted by the memory of a sun we will never see again? The trap is closing, and the only way out is forward, into a destination that might be just as cold and indifferent as the metal walls that have been their only world for a century. As the middle generation fades and the final generation takes command, they face a new and terrifying reality. They are no longer just a group of people, they have become a civilization in a tube. And as they prepare for the final approach, they realize that the most difficult part of the journey wasn't the distance or the radiation. It was the crushing weight of the centuries. The civilization problem is no longer a theory. It is a life-or-death struggle that will determine if the last few miles of the trillion-mile journey are even possible. The trap has done its work, and now, the final verdict of history is waiting in the light of a new sun. To reach a star like TRAPPIST-1, we have to move past the idea of a voyage and begin to talk about the birth and death of a civilization. TRAPPIST-1 is a dim, ultra-cool red dwarf star sitting 40 light-years away from our solar system. It is famous for hosting 7 rocky Earth-sized planets, 3 of which orbit in the habitable zone. To our telescopes, it is a beacon of hope, a potential second home for a crowded and tired Earth. But the physics of the journey is a staggering wall of time. At 10% of the speed of light, reaching TRAPPIST-1 takes 400 years. 4 centuries. This is not a mission. It is a 400-year-long experiment in human endurance. It is a span of time longer than the United States has existed as a nation. It is longer than the entire era of the Renaissance. To commit to TRAPPIST-1 is to ask a group of humans to build a society inside a metal tube, surrounded by an infinite, lethal vacuum, and maintain it for 20 successive generations with absolutely zero external support. This is the civilization problem, the realization that a starship is no longer a vehicle, but a floating fossil, and the people inside it are a society that must survive its own history before it can ever hope to see a new world. Think about the sheer, suffocating reality of a closed-loop civilization. On Earth, we live in an open system. We have a planet that recycles our waste, cleans our water, and refreshes our air through the massive, chaotic processes of geology and biology. We have room to expand, room to fail, and room to escape one another. But on a 400-year starship, the loop is absolute. Every atom of oxygen the crew breathes, every drop of water they drink, and every calorie of food they consume has been recycled thousands of times through the bodies of their ancestors. You aren't just living in a ship, you're living in a biological recycling machine where the molecules in your lungs were once the breath of a great-great-grandfather who died 2 centuries before you were born. This creates a psychological recycling fatigue, a deep subconscious claustrophobia where the crew realizes that nothing new ever enters their world. There is no new water, no new air, and no new genes. The ship is a finite universe, and after 200 years, the very walls of the vessel begin to feel like they are closing in, not because they are physically moving, but because the variety of life has been exhausted. The governance of such a civilization is a nightmare that no political theorist on Earth has ever solved. How do you maintain order in a population that has no escape? Democracy, as we know it, is a luxury of abundance. It requires the ability to compromise, to dissent, and to change direction. A starship in year 250 cannot afford a change of direction. It cannot afford a political movement that questions the necessity of the reactor's maintenance schedule. To survive 4 centuries, the ship must be an absolute, unwavering autocracy. It must be ruled by a technocratic priesthood, or an unyielding AI that prioritizes the machine's survival over every human right. The conflict between individual will and systemic necessity becomes a permanent state of war. A child born in Century 3 who wants to be an artist instead of an atmospheric technician is not just a dreamer. They are a threat to the oxygen levels of the entire species. The starship civilization must enforce a level of social conformity that would make the most brutal earthly dictatorships look like open societies. You are a cell in a larger organism, and if you do not function according to the blueprint, you are a cancer that must be excised. This leads to a terrifying phenomenon called generational stagnation. When every role is predetermined and every resource is rationed, the drive for innovation dies. Why invent something new when the ship's systems are already balanced to the edge of survival? The crew becomes a maintenance culture, a people whose only goal is to keep the lights flickering for one more day. Over 400 years, the scientific spirit that launched the mission would likely evaporate, replaced by a rigid, ritualistic devotion to the manuals left behind by the founders. The engineers become priests, performing the sacred rituals of the filter change and the coolant purge without truly understanding the physics behind them. If the civilization enters a dark age, a period of social collapse or knowledge loss in Century 2, they may never recover. They would arrive at TRAPPIST-1 not as explorers, but as a group of confused survivors, huddled in the ruins of a technology they can no longer repair, looking out at a new world with the eyes of a primitive tribe that has forgotten why it left home. Consider the genetic erosion of a 400-year voyage. A population of a few thousand people, isolated for 20 generations, is a biological ticking time bomb. Even with a library of frozen embryos and carefully managed breeding protocols, the lack of new genetic material creates a narrowing of the human experience. The ship kin, as they might call themselves, would begin to diverge from the humans on Earth. They would be smaller, adapted to the ship's low gravity and recycled nutrients. Their immune systems would be specialized for the specific, limited microbiome of the vessel. Over 4 centuries, the crew would become a new subspecies of humanity, one that is perfectly adapted to live in a metal tube, but may be fundamentally incapable of surviving on a real planet. The civilization problem is that by the time you reach the destination, you may have evolved into something that can no longer live there. The ship is no longer a bridge to a new world. It is a permanent biological cage. The cultural drift over 4 centuries would be absolute. Earth would transition from a memory to a myth, and eventually to a religion. The Blue Mother who sent them into the dark would be a goddess of impossible abundance, a place where water fell from the sky and the ground was covered in a soft green carpet. The crew's art, their music, and their stories would be obsessed with a world they have never seen and can never truly imagine. This creates a dual reality. They are living in a cramped, humid reality of steel and oil, while their minds are occupied by a fantasy of Earth. When they finally arrive at TRAPPIST-1, they aren't looking for a new world, they are looking for the old Earth. And this is the ultimate tragedy of the TRAPPIST mission. The destination system for all its rocky planets is almost certainly not Earth. It is a collection of red-lit, tidally locked worlds, bathed in the volatile flares of an angry dwarf star. The crew, having spent 400 years dreaming of a green paradise, arrives to find a red hellscape. The psychological collapse that follows would be civilizational in scale. The myth of the destination dies, and with it, the purpose that held the society together for 20 generations. We must also confront the resource entropy of a 4-century civilization. A starship is not just losing energy, it is losing complexity. Every time a tool breaks and is recycled into a 3D printer, a tiny bit of the original material's quality is lost. Every time a software system is patched by a 3rd-generation coder who doesn't fully understand the kernel, the ship's digital infrastructure grows more fragile. Over 400 years, the ship undergoes a slow rot. The high-tech marvel that left Earth in the 21st century arrives at TRAPPIST-1 as a patched-together relic, a collection of workarounds and good enough repairs held together by the sheer desperation of a crew that has no other choice. The civilization is living in a house that is falling apart faster than they can fix it. They are in a race against the structural limit of the ship itself. If the hull loses its integrity in year 350, the entire 4-century history of that civilization ends in a few seconds of decompression. A final, silent scream in the dark, just a few light years from the finish line. The civilization problem reveals the true cost of the stars. It isn't measured in money or even in individual lives. It is measured in the loss of human potential. To reach TRAPPIST-1, we are asking thousands of people to live and die in a state of permanent, restricted service to a machine. We are asking them to give up the variety of the human experience, the change of seasons, the meeting of strangers, the choice of a career, the freedom of movement, for the sake of a destination they will never see. The Starship is a time capsule that consumes its contents to keep moving. It is a civilization that exists only to deliver a message to a future that may not care. And as the ship finally enters the TRAPPIST-1 system, the 20th generation looks out at the dim, red sun and realizes that they are the only thing that survived the journey. The Earth is gone, the mission is old, the ship is dying, They are a civilization of ghosts standing on the threshold of a world that doesn't want them. As the final approach begins, the crew realizes that their endurance was just the first half of the battle. The second half is the realization that they might be obsolete. The weight calculation we discussed earlier is no longer a mathematical theory. It is a haunting possibility. What if during their 400-year journey, Earth developed a way to fold space or travel at 90% of light speed? What if a second ship, launched 2 centuries after them, has already arrived, settled the system, and built a thriving society? The civilization in a tube would arrive to find that they are not pioneers, but refugees from a previous era, carrying outdated technology and a distorted culture into a world that has moved on without them. The civilization problem is the ultimate confrontation with the reality of deep time. We are trying to outrun our own obsolescence, and the stars are the only witness to the race. There is a unique kind of heartbreak that only the laws of physics and the pace of human innovation can create. It is a tragedy not of failure, but of timing. Imagine, for a moment, that you are a member of the 20th generation aboard a Starship heading for TRAPPIST-1. You have spent your entire life in the service of a machine. You have breathed recycled air, eaten lab-grown protein, and maintained the failing cooling loops of a reactor that was built by ancestors you only know through flickering digital archives. You are the product of 400 years of staggering endurance. You are just months away from the destination. The red sun is finally a disk, and the 7 planets are no longer points of light, but worlds. You are preparing for the greatest moment in human history, the arrival of the first pioneers on an interstellar shore. But then the ship's long-range sensors pick up a signal. It isn't a pulsar or a background whisper of cosmic noise. It is a high-bandwidth, laser-tight transmission coming from the surface of the very planet you are aiming for. And the message is a greeting. In a language that sounds like a modernized version of your own, a voice says, "Welcome to TRAPPIST-1. We've been waiting for you for 50 years." This is the nightmare of the weight calculation, the cold, mathematical realization that in the race to the stars, the first to leave is almost never the first to arrive. In interstellar travel, speed is a variable, but the rate of human progress is a relentless acceleration. This concept, formalized by researcher Andrew Kennedy, suggests that for any distant destination, there is an optimal time to wait before launching. If you launch today at 10% of the speed of light, it will take you centuries to reach your goal. But if you wait 100 years, human technology might have advanced to the point where we can build a ship that travels at 20 or 30% of the speed of light. That second ship, launched a century after you, will overtake you in the dark. It will arrive at the destination, settle the planet, build a civilization, and be waiting on the docks to watch your primitive, rusted relic finally limp into orbit. You didn't fail the mission, you were simply leapfrogged by the future. The weight calculation is the ultimate sunk cost of the interstellar dream. It forces a civilization to ask a terrifying question. Is it worth launching a mission today if we know that the progress of tomorrow will make it redundant? On Earth, we are used to technology becoming obsolete. Buy a phone knowing it will be a relic in 3 years. We build a fighter jet knowing it will be outclassed in a decade. But when the product cycle is an interstellar voyage, the stakes are not measured in dollars but in human generations. To launch a multi-generational ship is to make a bet that human progress will stop the moment you leave. It is an act of supreme arrogance or supreme desperation. You are committing thousands of lives to a journey that physics itself tells you might be unnecessary. You are sentencing your descendants to a life of mechanical toil in a metal tube, knowing that they might arrive only to find that they are the technological equivalent of a horse-drawn carriage, arriving in a world of supersonic jets. Think about the psychological collapse of a leapfrogged crew. This is a trauma for which there is no terrestrial parallel. Every calorie of food grown in the ship's humid farm, every liter of water recycled from waste, and every hour spent scrubbing a radiator plate was a payment made toward a goal of being the first. That purpose is the only thing that kept the social fabric of the ship from tearing apart across 4 centuries. But when that purpose is stripped away, when the crew realizes they are not pioneers, but historical curiosities, the psychological foundation of the ship vanishes. They are the survivors of a 400-year siege that didn't need to happen. They are a lost colony that hasn't even landed yet. The realization that their ancestors could have just stayed on Earth, enjoyed the sun and the wind for another 200 years, and still arrived at the same time is a bitterness that no amount of mission success can sweeten. The ship becomes a monument to a tragic lack of patience. This creates a stagnation paradox for the people on the ship. While the crew is locked in a closed-loop system, struggling to maintain a technology that was frozen at the moment of launch, Earth is continuing its exponential climb. Every year on Earth, new materials are discovered, new propulsion physics are mastered, and new medical breakthroughs are achieved. But the ship is a time capsule. It is a piece of the 21st century drifting through the 25th. The crew cannot download a new engine. They cannot patch their DNA with the latest terrestrial gene edits. They are a biological and technological fossil, growing more obsolete with every light year they travel. The weight calculation turns the interstellar void into a mirror that shows the crew exactly how far they have fallen behind. They are reaching for the future, but they are being outrun by it. Consider the arrival greeting from the perspective of the people already on the planet. To the settled civilization at TRAPPIST-1, the arrival of the original generation ship is not a moment of scientific triumph. It is a historical reenactment. It is like an ancient steam engine rolling into a modern high-speed rail station. They see a ship that is falling apart, carrying a crew whose culture is a distorted relic of a forgotten era, running on software that is as primitive to them as a stone tablet. The people on the planet may look at the arrivals with pity or curiosity or even annoyance. The original pioneers, who expected to be the founding fathers of a new world, find themselves as refugees in a world that has moved on without them. They are the elderly ancestors, who have just arrived in a world run by their great-great-grandchildren. The power dynamic of the mission is completely inverted, and the dream of colonization becomes a reality of assimilation. The weight calculation also introduces the fear of the next breakthrough. Even the second ship, the one that overtook the first, lives in fear of being overtaken itself. This creates a civilizational paralysis. If we always wait for the next better engine, we never leave. But if we leave too soon, we waste the lives of the crew. This is the incentive gap of interstellar travel. It is a game of cosmic chicken played against the future. To reach the stars, a civilization must be willing to accept the obsolescence of its pioneers. It must be willing to say to a group of people, "Go now, even though we know you will be overtaken," because the act of going is the only thing that proves we can. This is a cold, utilitarian calculation that treats human lives as data points in a long-term trajectory. It is the ultimate expression of the civilization problem, the sacrifice of the few for the symbolic progress of the many. As the crew of our hypothetical starship processed the greeting from the surface of TRAPPIST-1, they realized that the void was not their only enemy. Time was the assassin, but it didn't kill them with radiation or cold welding. It killed them with progress. They are the victims of a universe where information and innovation travel faster than the machines we build. They stand on the bridge of their aging vessel, looking at the city lights on a world they thought was empty, and they feel a loneliness that is deeper than the interstellar dark. They are truly the people out of time. They have survived the biological cost, the power crisis, and the multi-generational trap, only to find that the prize was stolen by the very future they were trying to build. But there is one final rung on the ladder, a realization that is even more profound than being overtaken. Because as the crew looks at the lights of the civilization that beat them there, they have to ask, what happened to the ones who weren't greeted? What happens when a starship survives its journey, endures its centuries, and arrives at a star only to find nothing, no greeting? No city lights, no atmosphere, just the same silence they have lived in for 400 years. This is the silence of the stars, the final existential verdict for the starship that survives its journey, only to find that the universe is just as empty at the destination as it was along the way. And as the crew prepares for the possibility of a dead arrival, they realize that being overtaken might have been the better fate. There is a specific kind of terror in a silence that has been earned through centuries of struggle. Imagine that the weight calculation did not happen. Imagine that humanity did not develop a faster engine, and no one was waiting for you when you arrived at TRAPPIST-1 or Alpha Centauri. You are the first. Your ship, a scarred and flickering relic of a 20-generation voyage, has successfully decelerated. The long, agonizing years of digital rot and biological cost are over. You have survived the multi-generational trap and maintained your purpose through 400 years of darkness. The day of arrival has finally come. The crew, the children of the original pioneers, gather at the observation ports to see their new home, the planet that has been the singular focus of their civilization since before their great-grandparents were born. But as the first high-resolution images flicker onto the bridge screens, the room falls into a silence deeper than the interstellar void. There are no blue oceans, there are no green forests, there is no breathable atmosphere. There is only a scorched, airless rock, bathed in the violent ultraviolet glare of a star that never sleeps. This is the silence of the stars, the final, existential verdict for a species that spent everything it had to reach a destination that didn't want them. This is the ultimate anticlimax of the interstellar dream. We have spent decades on Earth scanning the sky for habitable worlds. We use the word Earth-like to describe any planet that is roughly the right size and roughly the right distance from its sun. But in the reality of the cosmos, the margins for life are razor-thin. A planet can be in the habitable zone and still be a sterile hellscape. It can have the right temperature but no magnetic field, allowing the stellar wind to strip away its atmosphere until the surface is as dead as the moon. It can have water, but that water might be locked under killum of ice or poisoned by toxic minerals. When a starship crew arrives at such a world after centuries of travel, they aren't just looking at a scientific disappointment. They are looking at the death of their purpose. They have reached the chosen land, only to find that it was a mirage created by the limitations of the telescopes they left behind 400 years ago. The psychological weight of a dead arrival is a civilizational extinction event. For 20 generations, hope was a survival system. The dream of the new Earth was the lubricant that kept the social gears of the ship turning. It was the reason parents taught their children how to fix the air scrubbers. It was the reason the crew endured the humid heat and the radiation rot. But when that hope is revealed to be a lie, the social fabric of the ship doesn't just fray, it evaporates. The civilization in a tube is suddenly faced with the reality that the metal walls they have lived in for 4 centuries are not a temporary bridge, they are their final destination. The ship is not a vehicle, it is their total universe, and that universe is failing. They are a civilization of ghosts, standing on the threshold of a world that offers them nothing but a closer view of their own extinction. Think about the signal of despair that the crew must send back to Earth. This is a moment of profound cosmic loneliness. They point their aging high-gain antenna back toward the sun, a star that is now just one point of light among billions, and they transmit the data. We have arrived, the planet is dead, there is no home here. That message will travel at the speed of light, crossing the 40 light-year void. It will take 40 years to reach Earth. By the time anyone on Earth hears their voice, the people who sent the message will have been dead for decades. They are talking to a ghost of an Earth that has already moved on, already changed, and possibly already forgotten them. The isolation is total. They are the only living things for light years in every direction, and they are trapped in a machine that is slowly, quietly, losing its battle against entropy. The crew is forced to confront the planetship paradox. For 400 years they have hated the ship. They have seen it as a cage, a prison of recycled air and narrow corridors. But as they look out at the airless, irradiated surface of the destination planet, they realize that the ship is the most hospitable place in the entire system. The metal tube, with all its flickering lights and failing pumps, is a paradise compared to the sterile rock below. This is a crushing irony. The very machine they were trying to escape is the only thing keeping them from being reclaimed by the atoms of the void. They cannot land. They cannot leave. They are in a state of orbital limbo, circling a dead world in a dying ship, watching the red sun rise and set over a horizon they will never walk on. The civilization aboard the ship must now decide what to do with the rest of forever. Some might suggest moving on to the next star, another 80 or 100-year voyage, but the ship is already 400 years old. Its hull is thin from interstellar dust erosion. Its reactor fuel is dangerously low. Its spare parts inventory is a collection of scrap. To move on is a death sentence. To stay is a slow decline. The civilization problem we discussed earlier becomes a civilization endgame. The crew might fracture into different factions, those who want to try and build underground habitats on the dead planet, and those who want to stay in the relative safety of the ship. But both paths lead to the same end. Without the massive industrial base of a living planet, they cannot manufacture the complex electronics and materials required to sustain high-tech life indefinitely. They are a sunset civilization, watching the last few sparks of human ingenuity fade in the shadow of a star that doesn't know they are there. This is the point where the mission's original scientific goals become almost laughable. Who cares about transit spectroscopy or gravitational mapping when your water recycler just lost another 2% of its efficiency? The crew stops being explorers and starts being scavengers of their own history. They might begin to dismantle non-essential parts of the ship, the research labs, the observation decks, just to find a few pieces of viable wire or a clean seal. They are eating their own world to survive. The ship becomes a sinking island in a sea of red light. The silence of the stars is the sound of a civilization that has run out of options, run out of time, and finally, run out of hope. We talk about the Fermi Paradox, the question of why we haven't heard from any other alien civilizations. Perhaps the answer is waiting at the end of every interstellar voyage. Perhaps the galaxy is filled with these ghost ships, the remains of civilizations that were brave enough to leave their homes, but found only silence at the other end. Perhaps the stars are a graveyard of ambitious machines that survived the journey but couldn't survive the arrival. Each one a tiny, cold monument to a species that reached for the light, only to find that the dark was deeper than they imagined. The Starship, once a pinnacle of human pride, becomes a drifting tomb, carrying the frozen data of a failed dream toward the end of time. As the lights on the ship finally begin to fail for the last time, as the reactor's heart gives its final cold pulse, the crew of the 20th generation looks out at the red sun one last time. They are not angry, they are not afraid. They are simply tired. They realize that the universe is not hostile, it is just indifferent. It doesn't hate them, it just doesn't care. The silence is not a threat, it is just the natural state of things. And as the air grows thin and the heaters go dark, the Starship ceases to be a machine. It becomes what it was always destined to be, a part of the void. The final verdict is no longer a distant possibility, it is the absolute reality of the moment. And as the last human heart stops beating 40 light-years from its ancestral home, the universe continues its slow, silent rotation, indifferent to the fact that for a brief, flickering moment, someone was there to watch it. The silence of the stars has claimed the mission. But as the ship drifts, a dead relic in a dead system, there remains one final question to answer. Not about the ship or the crew or the destination, but about the very nature of the effort itself. Was it a mistake? Was it a tragedy? Or was it the only possible ending for a species that refused to stay in its backyard? The final verdict of history is not written in the logs of the ship, but in the entropy of the universe itself. And as we move into the final section of our journey, we must look at the end of everything. The moment where even the memory of the starship is erased by the relentless march of time. We began this journey by looking at ourselves as infants playing in a backyard, terrified of wandering beyond the reach of our mother's voice. We looked at the International Space Station, a fragile miracle of engineering that breathes only because Earth is still holding its hand. We looked at Voyager 1, a fading ghost that is slowly losing its mind in the interstellar dark. And we have spent these last 2 hours walking the ladder of the stars, from the 40-year sprint to Alpha Centauri to the 400-year civilization trap of TRAPPIST-1. We have seen the digital rot, the thermal paradox, the biological cost, and the crushing weight of the weight calculation. We have confronted the possibility that even if we survive the journey, we might arrive at a destination that is as silent and dead as the void we just crossed. And now, at the end of all things, we are left with the final verdict. It is not a verdict written in the language of hope or despair, but in the cold, unyielding language of entropy. The universe is not a place that was built for us. It is a vast, ancient machine that is slowly, methodically, turning everything we build back into dust. And yet, the most profound thing about the starship is not that it might fail. The most profound thing is that we were ever brave enough to imagine it. To understand the final verdict, we must look at the second law of thermodynamics, the law of entropy. It is the only absolute ruler of the cosmos. It dictates that order always decays into chaos, that energy always spreads out until it is unusable, that every machine, no matter how perfect, must eventually break. A starship is the ultimate act of defiance against this law. It is an attempt to create a bubble of order, a tiny, flickering spark of life and logic, and push it through billions of miles of absolute chaos. But the universe is a master of patience. It doesn't need to attack the ship. It just needs to wait for the molecules to move, for the atoms to shift, and for the heat to bleed away. The final verdict of physics is that every starship we ever build will eventually become a ruin. Whether it reaches its destination or drifts forever in the dark, the end is the same. The machine stops, the air grows cold, and the silence returns. We are trying to build monuments in a world made of sand, and the wind never stops blowing. This realization brings us back to Voyager 1. We call it a success because it is still transmitting, 50 years after launch. But in the grand scale of the galaxy, Voyager is already a corpse. Its sensors are dim, its power is failing, and its message is a fading whisper. It is the first of our many interstellar ghosts. In 1,000 years, it will still be there, a cold piece of metal drifting through the dark, carrying a golden record of a civilization that might no longer exist. It is a tombstone for a species that wanted to be remembered, and perhaps that is the true purpose of every starship. We don't build them because we are certain we can survive the stars. We build them because we cannot bear the thought of being forgotten. The starship is not a vehicle of colonization. It is a message in a bottle, thrown into an infinite ocean by a species that knows its own island is eventually going to sink. There is a strange, haunting beauty in the failure of the mission. If a starship survives for 400 years, carries 20 generations of humans, and finally dies just short of its goal, was it a waste? To the cold eye of the weight calculation, perhaps. To the scientific mind looking for data, yes. But to the human spirit, that 400-year journey is the greatest story ever told. It is a story of a civilization that refused to stay in the backyard. It is a story of parents who loved their children enough to teach them how to fix a machine they would never see succeed. It is a story of the maintenance generation, finding meaning in the simple, daily act of keeping the air breathable for someone they would never meet. The final verdict is that the value of the Starship is not in the arrival, but in the endurance. We are the only part of the universe that has ever tried to fight entropy, and even if we lose, the fight itself is our greatest legacy. Consider the Stardust verdict. Every atom in your body, every drop of water in your blood, and every piece of silicon in your computer chips was forged in the heart of a dying star billions of years ago. We are literally made of the remains of an interstellar voyage that happened before the Earth was even born. When we build a starship and send it back into the dark, we are just returning those atoms to the place they came from. We are the universe trying to look back at itself. We are the cosmic dust that woke up and decided to build a machine to go home. If we fail, it is only because we are trying to do something that is fundamentally impossible, to keep a spark of life alive in a place that is designed for silence. But the fact that we even tried is the only proof we have that we are more than just a biological accident. We are a defiance. The silence of the stars is not a wall, it is a mirror. When we ask how long can a starship last, we are really asking how long can our legacy survive? And the answer is, as long as there is someone left to remember the dream. If we launch a ship today and it fails in 50 years, it is still a victory because it taught the next generation what not to do. If we launch a ship in 200 years and it is overtaken by a faster one, it is still a victory because it proved that we never stopped trying to get faster. The interstellar ladder is built out of the wrecks of the ships that came before. We climb over our own failures to reach the next rung. The final verdict is that humanity is not a spacefaring species yet, but we are the only species we know of that has the courage to be an infant in the dark, reaching for a light we can barely see. As you look up at the night sky tonight, remember that the points of light you see are not just stars. They are the sentences of survival we have been discussing. Alpha Centauri is a 40-year trial. TRAPPIST-1 is a 400-year civilization. Sirius is a generational handoff. Each one is a challenge that physics has set for us. The distance is a filter designed to see if we are worthy of the galaxy. And while the math says we are too fragile, while the biology says we are too weak, and while the engineering says we are too primitive, there is something else inside us that hasn't read the reports. Something that looks at the digital rot and the material grave and decides to build the ship anyway. That something is the reason you have watched this for 2 hours. It is the reason we keep scanning the sky. It is the reason Voyager 1 is still shouting its name into the void. The final verdict is this: a real starship will likely not last long enough to settle the galaxy. It will likely break, it will likely fade, and it will likely become another ghost in the dark. But the civilization that is brave enough to launch it, the civilization that is willing to pay the biological cost and endure the multi-generational trap, is a civilization that has already won. Because in a universe of infinite silence and relentless entropy, the only thing that truly lasts is the effort to reach out and touch the stars. We are a small, fragile species living on a pale blue dot, but we have built a dream that is larger than the void. And even if every ship we ever build ends as a steel sarcophagus, those tombs will be the most beautiful things in the universe. They will be the evidence that for a brief, flickering moment in the history of time, there was a species that refused to stay in its backyard. The lights of the International Space Station are passing overhead right now. Voyager 1 is 22 light-hours away, its heart growing cold. And somewhere in a laboratory or a garage or a child's imagination, the blueprint for the first real Starship is being drawn. It will fail, it will decay, it will eventually turn back into raw atoms, but it will go. And that is the only verdict that matters. The stars are waiting and the silence is deep, but the infant is no longer afraid. We are leaving the backyard and we are never coming back.